Hello everybody. Okay, so we ended on operations on radicals. We ended on simplifying radicals, and we're going to pick up right where we left off on operations on radicals. So let's start with, multiplication and division we already did. That's the idea that you can split the radicals apart or put them together. Okay, so just simply, in this case, multiplication and division is easier. Or actually, multiplication. Division we'll get to later. Multiplication, this is just your square root of A times the square root of B is equal to the square root of A times B. So let's put some actual numbers in here. Let's say that we had the square root of 10 times the square root of 5. This is just the square root of 50. Okay, and then we can reduce. So square root of 50, if we reduce it, and we have two ways that we can reduce this. We can either do our multiplication first and then take what we get as our result. Square root of 50 can be broken up. Perfect square that could be pulled out is square root of 25. Notice this is exactly what we did in the last video, where we had our perfect square under one radical and then whatever is left over under the other one. And this gives us 5 root 2. Okay, now we could have done this differently. We could have started breaking it up here. So I'll put that down here. Don't worry too much about this if it's not something that you feel comfortable with. But square root of 10 could be broken up into square root of 5 times the square root of 2. And then we have another square root of 5. Okay? And square root of 5 times the square root of 5 is just 5. It's square root of 5 squared. So I'm going to put in this middle step. You can leave it out. But what we have here is the square root of 5 squared times the square root of 2. And when you take a square root and you square it, the square root just goes away. Where this came from the square root of 10. So we just split up the square root of 10 into the square root of 5 times the square root of 2. And then we have 2 square roots of 5. So when we square that, when we multiply those, we get the square root of 25, or just 5. We can shorten it. Okay? So either of these is okay. The advantage of the second method is just that it's smaller numbers. Okay, so you're splitting this up essentially into all of its prime factors, and then any square roots that repeat, you just get rid of the square root and you make it the number. So square root of 5 times square root of 5 is 5. If we had had square root of 3 times square root of 3, you would have wound up with a 3 here. Okay, let's take one more example. Let's say that we have I'll put a 1 here, just so that you know that these are different examples. Let's say that we have the square root of 6 times the square root of 3. So this is the square root of 18. You're just doing 6 times 3. And then from here, we can simplify it in one of two ways. So the first way is simplify square root of 18. So this is square root of 9, square root of 2. 9 times 2 is 18. And this leaves us with 3 root 2. I'm not spending a lot of time on this because we did it with complex numbers. So this is just repetitive. Okay. The second option, again, it's up to you which one you like better. This one is not repetitive. We didn't do this before, but we're going to break up square root of 6 into its prime factors. So prime factors meaning all prime numbers that multiply out to 6. So square root of 6 is the same thing as square root of 3 times square root of 2. That's our square root of 6. And then we have another square root of 3. So we have 2 square roots of 3s. Again, I'm going to write this middle step. It is not necessary. That means that we have the square root of 3 squared times the square root of 2, which is also 3 root 2. So again, this square root of 3 square root of 2 came from the square root of 6. Okay, you don't need to write this. The reason why I'm writing it here is because a common mistake that people make is they say the square root of 3 times the square root of 3 is equal to the square root of 3. Okay, so just be very, very careful there. Square root of 3 times square root of 3 is equal to just 3. Okay, so that's multiplication. Okay, again, we've done this before. You did the reducing when we did complex numbers and we were taking the square roots of negative numbers. So that's why we did multiplication first, because it's already been done. Let's do addition and subtraction. So let's take an example and then we can be more specific about it. Let's just take something simple like 2 root 3 plus 5 root 3 minus 3 root 3. So notice we have addition and subtraction in this problem. That's because adding and subtracting radicals works the same way. Essentially what you're doing is you're just adding and subtracting your coefficients. Treat the square root of 3 like an x, okay? So it would be like 2x plus 5x minus 3x, okay? So 2x plus 5x is 7x, minus 3x is 4x, but instead of x, we're using 4 square root of 3. Okay, so this is similar to just adding and subtracting like terms. Sorry, then I didn't mean 7. I was getting ahead of myself. It's 2x plus 5x minus 3x. So notice these are all x, which means that they're like terms, and we're just adding and subtracting the coefficients. The reason why I say it's similar to and not the same as is because the square root of 3 is not a variable. It has a value, so we want to make sure that we want to make sure that we're not treating it like a variable. It has a value. It's just that when we add and subtract radicals, what's under the radicand, we don't do anything with it. It carries through, okay? So what we're doing is we're just adding and subtracting the numbers outside of the radical. If we have 8 times the square root of 7 plus 5 times the square root of 7, this is just 13 times the square root of 7. Okay, and I'm going to remind you that throughout this video, if you want to try something on your own, you should. After I write down the problem, just press pause, do it yourself, make sure that you understand how to do it, and then press play and actually watch as we work through the problem. Okay, so if I give you another addition or subtraction problem, which I will in a second, you're going to do the same thing. At this point, you should press pause and see if you can add or subtract. So let's take another example that's similar to this. Let's take 6 square root of 6 minus 2 square root of 6 plus 8 square root of 6 minus 3 square root of 6. So So 6 minus 2, notice we're only looking at the numbers on the outside. 6 minus 2 is 4. We're working left to right. 4 plus 8 is 12. And 12 minus 3 is 9. So we get 9 root 6. And you want to always, in everything that we do, you always want to see if the radical can be reduced. Okay, so I'll put that over here. So this is true for addition, for subtraction, for multiplication, when we do division. So you always want to check if the radical in your final answer can be reduced. Hopefully you can get this for any operation. This is something that we do. We always check to see if fractions can be reduced. We always check to see if radicals can be reduced. And I want you to notice something. In this case, the number under the radical, which if you remember is called the radicand, is the same, okay? Also, the index for all of these is 2, so that's also the same. We can add or subtract, okay, if the radicand isn't the same. We can add or subtract if the index isn't the same, okay? So there are actually 3 things that we're looking for. The radicand is the same. The index is the same. And the coefficients are like terms. And we'll see examples of this soon. So the coefficients are like terms. So in each of these problems, our coefficients are constants. They're just numbers. So we can add and subtract numbers. In other cases where we wind up with variables, it's going to be a problem. Okay? So let's take some more examples. We're going to start with just numbers, and then we're going to move on. So let's take, I'm going to number these again just so that it's easy for you to see what's the same example and what's not. Let's take square root of 12. Plus 5, square root of 3. So notice I'm not putting in any variables into the coefficients. But if we look here, the radicands are not the same, which means that as it is right now, we can add, okay? So I'm going to put this in a different number, in a different color. So we can't add yet. I'm going to underline this word yet. We may be able to add later. So we can't add yet because the radicands are not the same. So before we give up, we want to see if we could reduce the radicals, okay? And the whole point of reducing the radicals is to see if we can get the radicands to be the same. So in this case, the square root of 12 can be reduced. So the square root of 12, and when we say we can't add yet, we mean this part of it. Now the square root of 12 can be reduced because we can pull out a perfect square from the square root of 12. We can pull out square root of 4. Okay, and we can see here that now we do have radicands that are the same. Square root of 4, we're not going to leave it like that. We don't want to leave something as a radical if it's a perfect square. This is the same as we don't want to leave something looking like it's imaginary if it's not. Now the radicands are the same, we can add. So our final answer is 7 root 3. Okay, so here the radicands originally were different. We went to reduce one of the radicals. Okay, when we reduce the radicals, meaning what's on the radicand becomes smaller because we're pulling out a perfect square. Okay, when we reduce it, we got 2 root 3. Now the radicands are the same. The index is the same. The index is 2, so we can add. Radicands are the same, index is the same, and the coefficients are like terms. So because of that, we add the coefficients, we get 7 root 3. So again, we say the coefficients are like terms. That's because those are the only things that we can add. If they weren't like terms, for example, if it were 2x plus 5y, we can't add that. 2x plus 5y is just 2x plus 5y. So that's why we put in that third rule that we had on the previous page, where we say the coefficients are like terms, okay? Because in order to add the coefficients, they need to be like terms. Okay, let's take another example. Let's say that we have 4 times the square root of 8 plus 2 times the square root of 32. So this is another case where initially our radicands are different. We can't add it the way it is, but each of these radicands has a factor that's a perfect square inside. So we're going to try and reduce each radical. And again, if we reduce and the radicands are different, there's nothing that we can do. But if we reduce and the radicands are the same, then we can start adding. So the square root of 8 can be changed into the square root of 4 square root of 2. And the square root of 32 can be changed into the square root of 16 times the square root of 2. Now you can change square root of 32 so that it's so that you wind up with the same radicand of square root of 8, but then you're going to have to reduce in the end anyway. So I would reduce both radicals, okay? If they're not the same, try and reduce both of them. Square root of 3 could not be reduced. So now we have, I'm putting in an extra step here. You don't need this extra step. I just want to make sure that it's clear to everybody where our numbers are coming from. So square root of 4 is 2, so now we have 4 times 2. This is an equals. 4 times 2 times the square root of 2. And then square root of 16 is 4. So we have 2 times 4 times the square root of 2. And what that gives us it turns out, is 8 times the square root of 2 in both cases. So we have 16 times the square root of 2. And that's our final answer. Okay. Let's do another one. I suggest that for this one, you pause and you do it on your own first, just to see if you are starting to understand this. So we're going to take 5 times the square root of 28 minus 3 times the square root of 63. Notice we're subtracting now. Okay, so I would pause, try it on your own. Okay, square root of 28 can be broken up. We can take out a square root of 4. So we have 5 times the square root of 4 times the square root of 7. Notice I put the square root of 4 first. I make it a habit to put the perfect square first. You don't have to do that. I just like to keep everything in an order so that I'm not changing orders later on. But order doesn't matter because we're multiplying. Now, square root of 63, we can break up into square root of 9 times square root of 7. You can use the calculator to try and figure out what perfect square is a factor of 63. So now, again, we skip this step. We get 5 times 2 root 7 minus 3 times 3 root 7. And that means 5 times 2 is 10, so we have 10 root 7. And then 3 times 3 is 9. So minus 9 root 7. Now we have the same radicand, we have the same index, and our coefficients are like terms. So we can subtract and we just get square root of 7. And that's it. Okay, let's take a case that might be a little bit more complicated. Let's take a case where we have cube roots, just so that you know it can be done. So we're going to take 8 times the cube root of 16. So notice the way I wrote it. I left some space so that it's really clear that 3 is the index, okay? And 8 is the coefficient. And then we're going to add 7 times the cube root of 54. So we're doing multiplication between the 7 and the cube root of 54. Again, I left some space. I want it to be really clear that the 3 is the index, okay? So now we're going to break this up into perfect cubes. So if you're familiar with your perfect cubes, this is going to be a little bit easier for you, okay? Cube root of 16, there's 8 goes into 16. 8 is a factor of 16, and 8 is also a perfect cube. So now we have 8 times the cube root of 8 times the cube root of 2. Okay, 8 times 2 is 16. And again, if you're familiar with perfect cubes, you're going to know that 8 is a perfect cube. And then here for the 54, it turns out that 27, which is also a factor of 54, is a perfect cube. So one little hint if you want to try and do this quickly, is if you're adding these, we kind of intend for the radicands to be the same. So if this radicand is 2, divide by 2 first and see if what you get is a perfect cube. So 54 divided by 2 is 27. And notice what you get here then is 7 times the cube root of 27 times the cube root of 2. Okay, so we get the same radicand. That's why I say divide by 2. That's just a faster way of doing it, but again, you can always just keep dividing, and if you want to check on your calculator if it's a perfect cube, go back to what we said before about the fact that a cube root is also a power. So if you want to take the cube root of 54, that's the same thing as 54 to the 1/3, okay? And I'll write that down in just a minute. So the cube root of 8 is 2. And the cube root of 27 is 3. Notice you want to make it really clear what's the index and what's the coefficient. This is 16 times the cube root of 2 plus 21 times the cube root of 2. And now we do our check. Radicand is the same, index is the same, coefficient, like terms. And now we can just add. So 16 and 21 is 37. So our final answer is 37 times the cube root of 2. Okay, so just a few notes I want to make about this. The first one is cube root of 16 is the same thing as 16 to the 1/3 power. Right? We know this from the previous lesson. So if you want to check if something is a perfect cube, instead of just taking the square root, which is really nicely on your calculator, in some cases they don't have cube root on the calculator. So what you would do is you would take the 16, you would raise it to the 1/3 power. If you get an integer, it's a perfect cube, okay? 16 to the 1/3 is not, but 8 to the 1/3 is. 8 to the 1/3 is 2. 27 to the 1/3 is 3. Okay, so that's the first thing I want to mention. Second thing I want to mention is that every time that you do this, you do want to do a check. So you're going to say, do they have the same radicand? Check, they do. Do they have the same index? Check, these do. Are the coefficients like terms? Check, they are. So every time that you want to do this, you don't necessarily have to write it down, although on a test, this can be helpful because it tells me, remember on a test you're communicating with me, so it tells me that the radicand, that you know what to check for. You should be checking for the same radicand, the same index, and coefficients being like terms. Now in all of these examples, we've had coefficients that are numbers. Let's take a look at what happens when you have coefficients that might be variables, okay? So we're gonna do another 4 examples where we see this. And what this is gonna require is what we did in the last lesson where we were simplifying radicals, okay? So let's get started. This is all stuff that you already know. It's just it's all stuff that you already know. I'm gonna do this in black. We're just putting it all together. Okay. Everything that you've learned. Okay. So let's take the example 2 times the cube root of x to the 8th, y to the 6th. And now we're going to subtract 3y squared and then the cube root of 8 x to the 8th. Okay. This is a cube. Okay, that's a 3. Okay, so here our radicands are different. Now our index is the same. If our index were different, we shouldn't even bother, okay? If our index is different, we should stop where we are. There's nothing that we can do. But our index is the same, so we should look to see if we can simplify, okay? So let's just put this as a little note off to the side. If the index is different, don't try to reduce. Because even if you have the same radicand, it can't be added. Okay? Otherwise, you want to try to reduce. So here, notice this is the first case where our coefficients are not like terms right now. But it is possible that when we reduce the radicals, we will get like terms, okay? That it will happen in the end. So let's go through the process of reducing this. So we're going to do each one. If you remember, we do what is a perfect cube first, and then what is left over. So we have our coefficient, and then what's a perfect cube, and then what's left over. So we start with the x to the 8, and we say what's a perfect cube. So remember, what we're looking for is an exponent, the highest exponent less than 8, that's divisible by 3. So 8 is not divisible by 3. We go down by 1. 7, not divisible by 3. That 6 is divisible by 3. So we're going to pull out an x to the 6th. And what's left over is x squared. Now here, for the y to the 6th, 6 is divisible by 3. So the whole y to the 6th could get taken out and put in here. Which means there's nothing left over from the y's, okay? Now in our next one, what we are hoping for is that we wind up with a cube root of x squared. Let's see if that actually happens. So the cube root of 8, so 8 is a perfect cube. So we're going to put 8 in here. Okay, then we have x to the 8th. So just like this one, okay, x to the 6th is a perfect cube, so x to the 6th gets put under here, and then what's left over is x squared. Okay, there's hope for us, because in the what's left over, we have the same thing, but we need to make sure that our coefficients are the same first, okay, that our coefficients are like terms. So here, when we reduce, the cube root of x to the 6th, y to the 6th, remember you take the exponents and you divide by the index. So we get x squared, y squared. Cube root of x squared. Now over here, cube root of 8 is 2. So we have 3y squared, and I'm going to put a multiplication sign. We don't need it, but I'm putting it in there. 2, and then the cube root of x to the 6th is x squared. And then we have cube root of x squared. Okay. So let's take this and reduce it. Not reduce it, simplify it. We can multiply the 3 and the 2. Okay, so we just multiply the numbers. We get 6. And then we have y squared times x squared, which is the same thing as x squared y squared. So we're just going to rewrite it. And again, you can sometimes skip a step here or there. Which step you skip is up to you. If you wanted to skip this step that we're about to do, that's fine. Or I would even, if I were you, I would probably skip the step that we just did. So we have 2x squared, y squared. These lines just appear out of nowhere. Two x squared, y squared, cube root of x squared. And then we have minus 6x squared, y squared, and a cube root of x squared. And 2x squared y squared and 6x squared y squared, these are like terms. Everything is raised to the same exponent. We have the same variables. So you're looking at the variable. We have an x and it's squared. We have a y and it's squared. We're doing the same thing here. We have an x and it's squared, and our y is squared. And the radicand is the same. The index is the same. So we're going to go through the same checklist. Same radicand, same index, coefficients are like terms. How do we do this? In this case, we're subtracting. We subtract the coefficients. Remember, you're just subtracting the numbers. These are like terms. It's just like when we add the numbers here. Here we just worry about the numbers. So our final answer here is negative 4x squared, y squared, cube root of x squared. Okay, and I'll put in that checklist. I'll abbreviate it a little bit, but I want it in there. You don't have to do this every time, like I said. So same radicand, same index, and like terms. Okay, all three of those are right, so we can move on. Okay, let's do another example. So 5x squared square root of 27 AB cubed. No, sorry, cube root. I was looking at the wrong thing on my paper. Cube root of x y to the fourth minus 2y and a cube root of x to the 7th y. So the first thing that we check for is that the index is the same. That's true. We always check to see if the index is the same, because if it's different, we stop right there. Okay? Because it's the same, we can keep going. So now we're going to look to reduce our radicals. So this becomes 5x squared okay. The x, there's no number, there's no exponent that is going to be divisible by 3, because x to the first, not divisible by 3. If our exponent is less than our index to begin with, it just goes in the what's left over. So we just have an x. Now we look at the y. 4 is not divisible by 3. It's still greater than 3 though, so we now go through this process of taking the exponent and decreasing by 1. So 3 is divisible by 3. So out here, we're going to put a y cubed. And then what's left over? We took out 3 y's. There's 1 y left over. Now we're going to do the same thing with the other one. So we're going to have our perfect cubes. So in this case, 7 is greater than 3, so we're going to do that process. 7 is not divisible by 3. We go down by 1. 6 is divisible by 3. So we're going to pull out an x to the 6th. And then the what's left over, we have 6 x's. There's 1 left over. And the y is a 1, and that's less than 3. So we just have to put the whole y under the what's left over. And it's likely that we did something right here because we have the same radicals that are left over, and they should be the same. Okay. So now it's just a matter of simplifying our perfect cubes. We have a 5x squared. We take the exponent and we divide by the index, and we get y. And then we have cube root of xy. And then in the other one, we have 2. And I'm going to write it as x squared y. There's no reason to make it look different when it's the same. The cube root of x to the 6th, we take the exponent, divide by the index. 6 divided by 3 is 2. So we have 2x squared y. I realize it's 2yx squared, but remember the order doesn't matter. Okay, so we have 2x squared y and cube root of xy. And now we go through our checklist. The index is the same. The radicand is the same. We have xy and xy. And the coefficients are like terms. We have an x squared here and an x squared here. We have a y here and a y here. Okay, the numbers are going to be different. That's okay. Now we just subtract the numbers. 5 minus 2 is 3. So we have 3x squared y, and then the cube root of xy. And that's it. That's our final answer. Okay. Let's do another one. And with this one, I encourage you to try it on your own. Okay. So after I write it, pause. Do it on your own, see if you understand it. And this one we're going to add in extra thing. We're going to put the numbers under inside the radicand. But we're just dealing with square roots, so it's not that bad. 27ab cubed as our radicand, and then minus 6b, and then the square root of 12, a to the 5th, b. So I would pause here, try it yourself, and then you can press play again. The index is the same. If the index is different, we just sum. We have 5a squared. Perfect squares. 9 is a perfect square of 27. What's left over is 3. 9 times 3 is 27. So for numbers, we multiply. Here, the exponent of a is less than the index. So that just goes under what's left over. Then we look at the b. 3 is not divisible by 2. We decrease by 1. 2 is divisible by 2. So b squared goes under the perfect squares, and b to the first is what's left over. Now we're going to do the same thing with the second one. We're going to divide it up into perfect squares, and then what's left over. So 12 is divisible by 4. 4 is a perfect square, so we're going to put a 4 under here. And what's left over is a 3, because 4 times 3 is 12. Now we have a to the 5th. 5 is not divisible by 2, but 4 is. When we go down by 1, 4 is. So we have a to the 4th under the perfect squares. And then we took out 4a, so there's 1a left over. And b to the first, the exponent is less than the index, so the whole thing goes in what's left over. And we know that we did something right because we have square root of 3ab and square root of 3ab. So now we're going to simplify our perfect squares. We have 5a squared, square root of 9 is 3, and the square root of b squared is b. So So we have square root of 3ab, that's what's left over, it just stays where it is. And then minus 6b, square root of 4 is 2, square root of a to the 4th is a squared, and then square root of 3ab. Here, to simplify, we multiply the numbers, okay? So 5 times 3 is 15, a squared b times the square root of 3ab, and then minus 6 times 2, so again we're multiplying the numbers, is 12. And then here we also have an a squared and a b, so we're just going to write it as a squared b. The order of that a squared b doesn't matter, so we'll just make it look the same in both. And I'll put this again here, it's not on this page, so I'll put it here. Again, we check. The index is the same. If the index were different, you would have stopped after the first, before you did anything. The radicand is the same. And the coefficients are like terms. So now we just subtract the coefficients. 15a squared b minus 12a squared b is negative 3 a squared b. And then we have square root of 3ab. And that's our final answer. Let's do one more. This is the last one. We've done a lot of these. I'm sure you're a little tired of them, but you should be getting better and better at these. So again, you might want to stop the video just to try this on your own first. So we have the cube root of a to the 4th, b cubed, c squared, and then we're going to subtract 6 ab, and then the cube root of a c squared. So we can start by, again, we're going to reduce our radicals. The index is the same. So if the index is the same, we move forward, okay? So we have 7, and then we're going to divide this up into perfect cubes. And into our non-perfect cubes. So a to the 4th, 4 is not divisible by 3, but 3 is. So we're going to pull out an a cubed. And what's left over is an a. The 3 is divisible by 3. So we pull out a b cubed, and there's nothing left over. And here the 2 is less than 3. So when your exponent is less than the index, the whole thing goes under what's left over. And then we're going to subtract 6ab, and we're going to divide this. And here's the thing, there are no perfect cubes. So in this one, the exponents of a and c are both less than 3. Both less than the index. So the radical is in simplest form. You can't do anything with it. Okay, so let's keep going. We just have to do this one. So 3 divided by 3 is 1 for both of these. So this just reduces to 7ab times the cube root of ac squared. And then we have minus 6ab times the cube root of ac squared. And we go through our checklist because once we've reduced as much as we can, we're ready for the checklist. The index is the same, the radicand is the same, the coefficients are like terms. We have an a to the first and a b to the first. So we just subtract. And we get ab times the cube root of ac squared. Okay. Now I know I said one more example, but I just want to show you what it happens when the index is not the same. So let's say that we have 3a times the 4th root of a squared b to the 8th. And then we're going to add 2a squared times the cube root of a to the 7th b to the 10th. You stop here. There's nothing that you can do. You don't even bother going any further. So you can't do anything. The index is different. Addition and subtraction. Let's do division. So here's the thing with division. Division is just like complex numbers. You're not actually dividing. Okay? What's really happening is you're getting rid of the radicals in the denominator. So just like in complex numbers, when you want to get rid of the complex number, the imaginary in the denominator, here, you want to get rid of the radical in the denominator. And you do it in exactly the same way. So if you remember, in complex numbers, we multiply both the numerator and the denominator by the complex conjugate. Here, we're multiplying both the numerator and the denominator just by the conjugate. Okay. We don't call it complex because there is no complex part of it. There are no imaginary parts. Sorry. So both the numerator and the denominator. By the conjugate of the denominator. It's finding the conjugate is just like finding the conjugate of a complex number. So I'm going to put this in blue. This process is called rationalizing the denominator. So you should always rationalize a denominator at this point. So in the past, when you rationalize the denominator, okay, in the past when you had a square root in the denominator, and when I say in the past, I mean particularly when you were solving for the roots of a quadratic, okay, and you had square roots in the denominator, I said you can leave them. You can no longer leave square roots in the denominator. You must always rationalize the denominator. You have to always get rid of the square roots, okay? So let's take some examples. So first, let's just take a look at rationalizing the denominator at conjugates. So if we have 3 plus the square root of 2, the conjugate, remember we just changed the sign in the middle. 3 minus the square root of 2. If we multiply this, we get 9 minus 3 root 2 plus 3 root 2. And then square root of 2 times negative square root of 2 is just minus 2. Square root of 2 times square root of 2 is 2. And notice what happens. We just get 7. So this middle section here, this middle section just goes away. And this is the conjugate of 3 plus root 2. So when we multiply a number by its conjugate, you have the plus 3 root 2 in the middle and the minus 3 root 2 in the middle. That goes away, okay? Just like in complex conjugates, the imaginary numbers in the middle go away. Here, the same thing is true. The radicals in the middle go away. So we're just left with this nice whole number, okay? So let's take just some simple examples. Let's say that we have 2 over 3 plus square root of 5. So what we're going to do is we're going to multiply both the top and the bottom by the conjugate of the bottom. So we're going to multiply by 3 minus root 5 over 3 minus root 5. So the 2 gets distributed. Don't forget to distribute. 6 minus 2 times the square root of 5. And then on the bottom, everything in the first gets distributed to everything in the second. So we have 9 minus 3 root 5 plus 3 root 5. You can leave this out in the future since you already know it cancels. And then minus 5. Remember, square root of 5 times square root of 5 is 5. And it's a minus because we have a plus root 5 and a minus root 5. So now we have 6 minus 2 root 5 over, I'm going to put 9 minus 5. You can absolutely skip this. 6 minus 2 root 5. We can't do anything with. One has a radical, one doesn't. This gets left. The only thing that you want to check for is whether every term is divisible by a number. And here, every term is divisible by number. Every term is divisible by 2. So we can divide 4 by 2 and we get a 2. 6 by 2, we get a 3. And 2 by 2 gives us a 1. Okay? You always want to do this, but this you already know. So what we get as our final answer here is 3 minus square root of 5 over 2. Let's do another one. Let's say that we have 6 plus the square root of 5 over square root of 2 minus square root of 5. So nothing changes here, okay? We're still going to multiply by the conjugate of the bottom. The fact that there's 2 terms at the top doesn't change anything. So we're going to multiply both the top and the bottom by square root of 2 plus square root of 5. Conjugate, all the conjugate does is change that sign in the middle. Now again, you can go straight on the bottom if you understand that it's 2 minus 5, that's fine. 6 times the square root of 2 is 6 root 2. 6 times the square root of 5 is 6 root 5. Then we have the square root of 10, because square root of 5 times square root of 2 is square root of 10. And then plus the square root of 25. On bottom, we have 2. Remember, square root of 2 times square root of 2 is 2. Then we have plus square root of 10 minus square root of 10, and then minus 5. Okay? Remember, multiplication of radicals. We just multiply the numbers under the radical. That's where square root of 10 is. Okay? And then square root of 5 times square root of 5. One is positive, one is negative. That's why it's minus. Okay? It's always going to be a minus for that reason, because we're always making one positive and one negative. Square root of 10 minus square root of 10 cancels. So what are we left with? 6 root 2 plus 6 root 5 plus the square root of 10 plus 5. Don't leave something as a radical if it doesn't have to be. And then 2 minus 5 is negative 3. And we can't do anything with this. Okay? We have different radicands, and square root of 10 can't be reduced. So as soon as the radicands are different, your numerator is just really long. That's okay. There's nothing wrong with that. Okay. Let's take another one. Let's say that we have 3 plus the square root of 7. This will be our last one. And then 5 minus the square root of 7. So the process is the same. We're just going to multiply by the conjugate of the bottom. And now we just distribute. 3 times 5 is 15. 3 times the square root of 7 is plus 3 root 7. Square root of 7 times 5 is 5 root 7. And then square root of 7 times square root of 7 is 7. Be careful about that. Then we do the same on the bottom. We have 25. And then we have plus 5 root 7 minus 5 root 7. That should always happen. It should always cancel like that. And then we have a minus 7 again. So our 5 root 7s cancel. Do not cancel out these 7s. Remember, that is an order of operations mistake. Okay? You can't cancel out the 7s. So we're going to add. 15 and 7 can be added. We get 22. Here we have the same radicand. So because we have the same radicand, index is the same, and the coefficients are like terms, we can add these. We get plus 8 root 7. And then 25 minus 7 is 18. Okay, so we can add here. We're adding like terms. 15 plus 7 is what gave us the 22, and the 3 root 7 plus 5 root 7 is what gave us the 8 root 7. And then we're going to do the same thing. We're not going to say we're done until we make sure that we don't have a common factor for every term, and we do here. Everything is divisible by 2. So we're going to divide everything by 2. We get 11. 22 divided by 2 is 11. 8 divided by 2 is 4. Notice we don't divide the square root. And 18 divided by 2 is 9. That's our final answer. We do not divide the square root. We're just dividing the coefficient. Okay? This is our final answer. So that's operations on radicals. So the last thing that we're going to do in the next video is equations with radicals, and then we'll be done with radicals, and we'll move on to, we're going to do more with exponents from there. Okay, that's it. Thank you.